This video is the fourth in a series analysing historic Formula 1 cars using CFD. The McLaren MP4 is a legend of the sport, the most dominant car in its history. It hardly needs an introduction. Everything just came together, probably the best driver pairing the sport has seen, a solid Honda engine, and a team that had just a few years earlier produced the previously most dominant car, the MP4 too. There's the forever repeated fact that it won 15 out of the 16 races during 1988. Similarly, taking 15 of the 16 poles, 13 were for Senna alone, establishing him on a path to greatness. Almost anyone digging into the history of this sport will quickly come across this car. Here I wanted to develop an understanding of its aerodynamics through CFD. However, to make sense of CFD simulation models, context is not just important, but necessary. With all the myths surrounding this legend, research was conducted to provide this context. This way the simulations can make sense and maybe even rein in some of the myths. The McLaren team that developed this car was just 17 strong, led by owner Ron Dennis and technical director Gordon Murray. Securing Honda engines from the reigning world champions Williams, McLaren with designer Steve Nichols set to build a low and efficient car. Unlike the MP4 the MP4 is not an innovative car. It is mostly known for being a low-slung car. The aerodynamics are still basic with the established front and rear wing, but it had a second-generation diffuser concept developed from its predecessor. From the vast amount said about this car, a number of key insights help guide this analysis. There are 3 takes from an assortment of media that are particularly useful. They may not be directly useful for what they specifically say, but for what they don't say. As the analysis progresses, I'll refer back to these, and it should become clearer why I chose them and not some that are more direct. The first is from Neil Oatley, Prost engineer in 1987 and 88, in a McLaren video. He spoke about the first test where he was pleased that the MP4 had gone 2 seconds quicker than last season's MP4 in the first few laps and had cured its difficult handling tendencies. The second is from Steve Nichols, in the Haynes McLaren MP4 owner's manual, describing the extent of effort that went into lowering the centre of gravity. Nichols stated that lowering the centre of gravity by 10 mm gave about 0.3 of a second per lap, and for the MP4 it was lowered by 30 mm, meaning 1 second was gained. Lastly, from Gordon Murray, a few years ago at his car exhibition speaking to WTF1, where he stated he knew by the downforce numbers coming from the wind tunnel that they were going to have a good car. The strange thing about this car, it is really difficult to get a straight answer as to why the MP4 was such a dominant car, which still provides plenty of room for debate. So paraphrasing these 3 insiders, I think it is telling. They were all in some way suggesting that it was a good handling car. For Murray mentioning its aerodynamics when the design focus wasn't on its aerodynamics, likely means that it wouldn't probably need great aero to be competitive. He refers to the Brabham BT55 as a lineage on the number of occasions for its lowness. Maybe it suggests it had rubbish aero. I mean, I have seen the car without a diffuser, so the floor is essentially just coming for the ride. I suspect I among many, thought its famous ultra-low bodywork was for the purpose of exposing the rear wing to free-stream air. However, it wasn't necessary. The shape of the rear bodywork was already established on its predecessor, the MP4 and then previously on the Williams FW11. The gains for the MP4 were said to be large, but then any progress for the MP4 was minimal, according to Nichols. Interestingly, one of the technologies that allowed the more shrunken bodywork was CAD, which was first deployed by Williams for the FW11, establishing the future of digital technologies in this sport. To summarize this car from the research, it is probably the last of the mechanically orientated cars. The low-slung car was a product of moving the centre of gravity as low as possible with the engine and gearbox developments to match this strategy. There was aerodynamic development, particularly with the diffuser. It was much more an evolution of the McLaren team's previous cars than a radically different concept. Now the experiment. Overall there was 8 simulations run for this experiment. These consisted of 5 runs for the MP4 and 3 for the MP4 all in different ride height configurations. Over the season, the MP4 ran 3 rear wings, one for low, medium and high downforce. Only the medium was tested here. The floor and diffuser it ran did not change during the 1988 season. It was a diffuser developed for the season and a step change in concept from the MP4-3, which was only different with some strakes added to the MP4-2's diffuser. Murray was clearly more confident than Nichols, who thought that the downforce numbers should be okay, but he didn't really know until the car was tested at Imola. The analysis of the MP4-4 starts with the ride height at the same 60mm that was used for the previous BT52 and MP4-2. The exhaust exits into the diffuser, so that was initially tested at 60 meters per second, then it was set to 120 meters per second where it stayed. The flat ride height was lowered to 40mm and 30mm, which was repeated for the MP4-2 to compare old versus new. It also answers a query I had with that car, as to why the diffuser design wasn't changed over the 3 seasons it ran. Strakes were added for the MP4-3, but there wasn't a change in its aggressive angle. From there, 2 degrees of rake were added to 2 different ride heights to reflect the Imola test notes in the Haynes MP4 owner's manual. The first simulation is used as a direct comparison to the last experiments. It is to establish a comparison to the mentioned research along with the previously tested cars. I improved the color maps because this was needed, also because the energy gradients are going to get higher with the later car models. Using a dark color at 0 creates a boundary between the high and low pressure regions. On a positive scale, it allows emerging disturbances from turbulence in the Vortex of the X movies to be seen. Other than this, the range of colors makes it easier for gradient identification. We start this analysis with the rear wing, as it is a theme that Murray had emphasized with the low-slung body. It had a particular emphasis with the Brabham BT52 analysed in the first video in this series. This then forms the basis of a direct downforce comparison of the BT52 and MP4-2C's rear wings. They each produced 953 newtons and 1050 newtons respectively, compared with the MP4-4's 1267 newtons. It's a gain of 33 and 21%. A measure of efficiency, the lift-to-drag ratio went from 3.47 to 3.84 to 3.77 for the MP4-4, an 8.6 and massive 33% increase. To add, the lift-to-drag ratio is about right for a 3-element wing of this type. Something close to an efficiency of 4 is what I understand to be correct, going by the reading I have done. Playing around with the profiles and element position should see some improvements. But the principle stands that the more laminar flow, the more efficient the aerodynamic device. Changing the top radiator exits the MP4-2 had to having side exits like the FW11, MP4-3, and thus the MP4-4 is a much better solution. It reduces the frontal area and cleans up the airflow to the rear wing. The pressure maps of the MP4-2C and the MP4-4 showed how dramatically different these cars are, despite the wheelbase being almost identical. The assumption would be that the rear wing should show differences. It does, with high values on the top and low values underneath, particularly on the third element. The floor for the MP4-4 is not performing as expected in this configuration. That ends up changing. The wall shear stress maps illustrates the direction of the airflow forming lines as it moves over the body. These apparent lines are different shear force values created by small disturbances across the surface. On top of the body, the MP4-4 has a lot less going on, which is good for efficiency. Then underneath, the diffuser has very different characteristics as seen by the flow lines. On top of the wall shear stress map, I placed Q iso volumes. These are used to expand on the flow structure seen on the body into 3D space. They are similar to the 2D vorticity maps tracking the rotational velocity of the air in the X movies. Mapped over these ISO volumes are kinetic energy values, mainly to try and see the ISO volumes more clearly, because they are getting a bit busy, particularly in the diffuser. I'm going to need to work out a better method to visualize the flow structures in the diffuser. Creating a time series would work, but that may take a week of computation and all my storage. A change to the vorticity color map makes it easier to see the emerging turbulence from the dark background, therefore representing the disturbed air more effectively and illustrates how much it is impacting the rear wing. As you can see, by the time the air reaches the rear axles, the turbulence above the MP4 is much less and lower than the MP4-2. As a result, the low pressure under the rear wing has a greater volume for the MP4-4. The velocity is subsequently higher and the wake from the rear wing is a different shape. The second test, the exhaust outlet velocity was changed to 120 meters per second. Previously on the MP4-2B, there was an 8.5% increase in downforce going from 60 meters per second to 120 meters per second on the body alone. Here with the MP4-4, the body is clearly outside its working range. The increase was about half that with 4.6%. I would expect that if the floor and diffuser are working better, there should be a further increase in the downforce numbers. Aerodynamics at the front of the car were a product of the narrowing and stiffening of the chassis. The fact that the nose is narrower, allowing a greater front wing surface area, was more of a nice byproduct of this design. Comparing the experiment results gave the same amount of negative lift. Though there is an additional 36 newtons, it was done with significantly less drag. The efficiency ratio went from 8.4 to 10.6 or 26%. That then increased to 12.9% or 65% when the car was lowered. Most of this improvement is due to the 17% more wing width, but the body itself is producing a measurable amount of downforce, skewing its numbers. Due to the aerodynamics being maybe not a second thought, but a necessary add-on, it wasn't the strongest on the grid that season. Nick Worth and Adrian Newey muttered to each other about the primitive Aero after the first test. However, compared to its predecessor, a significant amount of work must have gone into designing the diffuser. But it is highly unlikely that the Aero provided the performance edge. It is more likely that the design emphasis provided an excellent platform for the aerodynamics to work. If the center of gravity is lower, there would tend to be less body roll. If there was less body roll, then the ride height can be lower. If the ride height can be lower, the floor would have better interactions, creating more ground effect downforce. It was the last experiment with the MP4-2C. I was flummoxed by the fact that over 3 years, maybe 4 seasons, that ran the same floor and diffuser. Here, changing the ride height of both the MP4-2C and the MP4 gives an insight into the diffuser configuration, because the MP4-4 at 60 meters per second produces almost half that of the MP4-2C. The MP4-2C and the MP4-4, even when the body is only producing half the downforce, the total downforce is basically the same. It's just done much more efficiently. The lift-to-drag ratio increases from 1.51 to 1.84, or 22%. Most of this is just reducing drag, 17% in this case. So the aggressive diffuser angle on the MP4-2C works well at 60mm ride height, the MP4-4 doesn't. This is the first indication why the MP4-2 never changed its diffuser angle to something that I thought should have started looking more like the MP4-4. The fact that the newer floor has 486 newtons less means that there is something fundamentally wrong. Lowering the ride height to 40mm increases the body's downforce to 1062 newtons, much to my relief. Lowering it again to 30mm gave 1129 newtons. However, something removed 170 newtons from the rear wing, and paradoxically there is also less in the front wing. I'll have a go at explaining this at the end. The plot comparing both the MP4-2C and the MP4 relative to the ride height shows that the diffuser design is critically affected by how much air is entering from the floor. From these numbers, it seems like the older MP4-2 has a better configuration even at the lower ride height. However, the absolute downforce numbers may be deceiving. These plots from the mouth of the diffuser directly shows that the floor is working much better than the newer design. The MP4-2 peak low is at 1650, about 40% less than the MP4-4 at the same height. One of the force outputs available is moments around a chosen point, in this case the rear wheels. This can be used to calculate the center of pressure or force. Here I think it provides an insight because I was skeptical about the outright numbers suggesting the newer design wasn't better, but the pressure map on the floor was better on the MP4-4. A large area of low pressure is present in the mouth of the diffuser, and the diffuser itself seems to be accelerating more air through it, at least in the middle channels. But the center of pressure is 1.09 and 0.65 meters ahead of the rear axle when comparing the MP4-2 to the MP4-4. So it seems like the wider nose on the MP4-2 has a significant influence on the numbers. So some of the downforce lost by the front wing is being picked up by the body. Without digging too deeply and finding out exactly how much the nose is contributing to the plot and downforce location, it gives a good indication of the nose's influence. On the pressure plot, there seems to be much more low pressure color difference at the front. Say if you take 10 to 15% of the MP4-2 front wing downforce and subtract it to the floor, it starts to make a little bit more sense. But to find out, really the nose needs to be sectioned like the wing. Considering the front wing and nose are integrated for the first time in 1988 with a March 88 one, this may allow retesting. Still, these numbers for the MP4-4 seem a bit low and may require a change in geometry, but I don't think there will be a dramatic increase. This diffuser works much better with a lower ride height, but fundamentally the rear wing and the diffuser interaction is weak. Pulling more air out from the floor may be limited by the external flow. Adding a lower beam element like the FW11 would do more than a change in the diffuser geometry here. However, the fact is that the floor of the MP4-4 works because the diffuser works and works better than the MP4-2. It is unlikely that just because the floor works this car was as fast as it was. We know that the car had excellent low mass distribution. So fundamentally being able to consistently run a low flat car would be a significant benefit, even by just having less body roll. Therefore it is more likely the mechanics of this car provide a superior aerodynamic platform. This is the idea with a lot, if not all, band suspension developments in Formula 1. They were to provide a better aerodynamic platform. Active suspension, tune mass dampers, and hydraulically interconnected front and rear suspensions, or fric systems, were each a way of supporting the aerodynamic platform. Having established the comparative increase in performance of the MP4-4 in these simulations, we can expand on real-world references. The Haynes' McLaren MP4 Owner's Workshop Manual has images of the setup notes from the first test in Imola. These notes are simple but insightful. They provide the ride height along with other basic setup parameters for what was a remarkable test for a remarkable car. Turning up on the last day of testing when the rest of the teams had been running for days, it took just 17 laps for Prost to lap 1 second quicker than everyone else. I'm guessing that was what Oatley was referring to in the McLaren video. By the end of the day of testing, it had lapped 2 seconds quicker than everybody else in the hands of Senna. Conveniently, the test notes have the ride height, with the front at 1 11/16 of an inch, and the rear at 2 3/16 of an inch. About 43mm front and 55.5mm rear. That is about 0.2 degrees of rake. This was lowered to 1 inch at the front and 1.5 inches at the rear. However, it could read it was lowered by this amount. After Prost stated the car was bottoming too much, bump rubbers were increased. But whatever the ride height, the idea would be that the car was running lower and with more rake than the previous simulations. So 2 additional simulations were run at 0.2 degrees rake. The first run was with 38mm front and 48mm rear, which gave similar results to the test run flat at 40mm. The total negative lift is 2,990 newtons, 1,038 newtons coming from the floor. The center of pressure shifted forward slightly by 117mm to 665mm forward of the rear axle. The last simulation of the car was with rake and a lower ride of 21mm at the front and 31mm at the rear. With the simulation airspeed at 50 meters per second or 180 kilometers per hour, this would be about right, maybe still a little high. Here the resultant downforce numbers are significantly higher. Overall, the car produces 3,560 newtons, with the floor contributing 1,469 newtons, or 41%. Seen for the first time on the full pressure map, there is a proper low pressure region at the leading edge of the side pods. With the height of the floor combined with the rake, the whole floor is now acting like a ground effects device. Ignoring the middle plot, it's just there to randomly show why total pressure is a poor way to measure downforce. The pressure plots from the diffuser's mouth of 30mm ride height and the last test with the low front show the peak pressures are the same but distributed differently. The total area of low pressure in both the pressure map and plot is larger for the body with rake. This also represents a 30% increase in downforce just by lowering the front by 10mm. Lastly, these X movies. Three different sets are shown: vorticity, pressure, and velocity. The vorticity is configured such that the turbulence is visible in the emergence of colour from the dark base. As seen before, the MP4 creates a lot more disturbance. At the lower floor heights, there can be seen flow structures linking the floor and the ground. Boundary layer growth can be seen with this set and the velocity set. The front wing vortices can be seen blowing up before they impact the side pods. Also shown is how lowering the front wing and the end plates close to the ground, the vortex becomes smaller and weaker. For whatever reason, the length and intensity of the vortex coming off the front wing at 30mm dramatically affect how much downforce is created by it. This has a flow-on effect then to the rear wing by slowing the air that is travelling underneath it, reducing its effectiveness. This coincidentally happens at this speed and ride height, removing 170 to 180 newtons from the wings. The fact that the vertical structure is impacting the side pods like this is not ideal. But seeing the reduction in downforce is most likely instantaneous and wouldn't affect the car's performance. It's probably just a remarkable coincidence as seen here, because changing the speed or ride height would make this phenomenon disappear like the other foreruns. Spotting it in the X movies is best done with the X velocity, where the shape of the flow is slightly different forward of the side pods and rear axle. Management of the front wing vortices will be subject to future videos as teams begin to manipulate flow structures more deliberately around the front of the car. So concluding this analysis, taking on the McLaren MP4 is a daunting task considering its reputation. The legend has its myths for sure. Some of these myths were firmly embedded in my memory, and some of these have now been shattered. But in their place I could admire the overall package that was delivered, because the Aero wasn't the best on the grid. Like the Ferrari F2002, Williams FW14 and the Mercedes W11, they were just fast cars. Their overall package delivered dominant performance, just like the McLaren MP4.